Let's talk about something called a rate law. A rate law is an expression that shows the relationship between concentration, the rate of reaction, and what's called the rate constant. And it does have a general form. This is a typical rate law expression. Now, the rate law is experimentally determined, and I can't emphasize this enough. You can't just look at the balanced equation and write what the rate law is. I could write it as rate equals that rate law constant times the concentration of A, or maybe it's A squared, or maybe it's A squared times B, or maybe it's just the B. So you have to be given data that supports and matches the rate law. Notice that only reactants are in rate laws and that K is the constant. So you will be given a set of data points, and then from that you will have to write the rate law. There are many orders of reactions, but for the AP test there is only these three. So a zero order reaction, first order, and second order. You can tell what the order of reaction is by the exponent. So in this first one, my exponent is 0. And remember, when anything is raised to the 0 power, then that just means it's a 1. So you could also represent a zero order reaction as rate is equal to the rate law constant. If my exponent is a 1, and it's usually not written, then that is a first order. And if it is a 2 or the exponents add up to 2, then that would be a second order of reaction. And one way to find the rate law constant is to find the slope if you have a graph. Determining reaction order. So here's my general rate law, and you look at those exponents. So the reaction is the X order in A and the Y order in B. And the overall order, you would add those exponents. Now remember, these are experimentally determined, and you cannot get X and Y, or these exponents, from a balanced chemical equation. So on this problem down right here, what is the order reaction for rate equals K times the concentration of A squared times B? Well, I would add the exponents, and so my order of reaction in this case is 2 plus 1. This would be a third order reaction. A question like this could be asked, but if you had anything from a set of data points or from a graph, it would only be zero order, first order, or second order. So you would not have to find a third order because it gets really complicated the more you get. The formula for rate order from experimental data, you are going to use something that looks like this. Notice that I really just take the rate law and then I put them on top of each other. So I have my first set of data points. I'll write a rate law for using this format, and then I have my second set of data points, and then I'll put them equal to each other, and then we'll cancel out what is the same, and we will end up with what our rate order is. Down here I have a table that shows the relationship with time, the concentration of bromine, the rate, and it also has the rate law constant. And what I want you to see is that the rate law constant is just that. It is a constant. So this is experimentally determined, and you can see that it's about the same value. So when you look at that rate law, that is associated with a certain reaction. Let's start off with an example for a zero order reaction or a zeroth order reaction. And I'm telling you this is a zero order reaction, but let me show you how you could figure out it was a zero order reaction. So I'm going to be given a data table, and then I'm going to write a rate law for two of my experiments. And I'm just going to put them on top of each other. And it doesn't matter which ones you pick. And I think I'm just going to pick number 1 and number 2. And just to make my math easy, I'm going to make it so that the larger numbers are on the top and smaller numbers are on the bottom. So I'm going to put experiment 1 on the top, and I'm going to put experiment 2 on the bottom. And it doesn't really matter what goes on top and what goes on bottom. You can still figure it out. It's just the math is a little bit easier if the larger numbers are on the top. So I'm going to have the rate of experiment 1 equal to the rate law of experiment 1 times the concentration of A raised to the x. And it's that x that we want to solve for. And I am going to divide this by my second experiment. So the rate of my second experiment equals my rate law of the second one times a to the x. And I'm going to put in my numbers. So what do I know? I know that I have 2.0 times 10 to the minus 3 is the rate for experiment 1. And the rate for experiment 2 would be 2.0 times 10 to the minus 3. And then on this side, I have my rate law constants. And then I put my concentrations in. So I have 0.4 to the x, and I have 0.2 to the x. So let's eliminate what is the same. So I have these crossing out, so that equals 1. So I'm going to bring my work up here. So I have 1 is equal to, I'm going to cross my k's out. And so I'm left with 0.4 to the x divided by 0.2 to the x. And I end up with 2 to the x. So you have to ask yourself, 1 equals 2 to the x, what does x have to be? And in order for that to equal 1, I would have to have x be equal to 0. Because that's the only way to solve for that equation. 1 equals 2 to the x, x has to equal 0. So I find that when I go to write my rate law, I would write rate equals rate law constant times the concentration raised to the 0. Or, because that's just equal to a 1, you would go rate equals k. So that's how you find out what the rate law is from experimental data. So in zero order reaction, the concentration decreases with time, and the slope is the rate. And if you were to graph rate versus time in a order reaction, the rate would just stay steady. So, and that's one thing that you can see, that doesn't matter what my concentration is, my rate is always the same. So it doesn't matter what A is, I'm always going to get the same rate, 2 times 10 to the minus 3. So that's one way to, well, a couple different ways to spot a zero order reaction. Go ahead and do this math, which I encourage you to do every single time. And also just notice that the rate doesn't change, no matter what you do to the concentration. Okay, let's look at a first order reaction. And again, I'm telling you that it is a first order reaction, but this is how you would figure it out just using the data table. And so I'm just going to pick 2 experiments. I'm just looking at A, and I want the larger number on the top, so I'm going to use, I guess I'll just use the first 2. It doesn't really matter which ones you use. So I'm going to put experiment 1 on the top and 2 on the bottom. So I'm going to end up with rate of the first one equals the rate law constant times A to the x, and then I'm going to divide it by the rate of the second one. So those are all set up. Now I just plug in what I know. So my rate of the first one, it's 8 times 10 to the minus 3 divided by 4 times 10 to the minus 3. And then I get my K1 over my K2. And my concentration is 0.4 to the x and 0.2 to the x. So I just fill in all my information. On this first one, this cancels out, and I am left with a 2. I'll just put that answer above. And then on the top, I can cancel out those rate law constants because it's the same equation. And I get 0.4 divided by 0.2, I get 2 raised to the x. And I have to solve for what x is. And I know that x equals 1, because that will make that equation true. So this is a first order reaction. When I go to write it, it's going to look like this. Rate equals the rate law constant, and then the concentration of A raised to the 1 power, which you don't have to write the 1. If you did write the 1, they won't mark you wrong. Let's look at a first order reaction. If we look at its graphs, first of all, the concentration versus time. You can see that the concentration decreases with time, and that is because the reactants get used up. Remember, we only put the reactants in the rate laws. So we're going to see those reactants disappear and because they become products over time. And then let's look at this graph. This graph is the natural log of the concentration versus time, and I get a straight line. One of the ways that you can tell that you have a first order reaction is when you graph the natural log of the concentration versus time, it's a straight line. And notice that the slope is the rate law constant, and it does have a negative slope. In a zero order reaction, you get a straight line just graphing the concentration versus time. But in order to get a straight line in your graph with the first order reaction, you have to use the natural log of the concentration versus time. And that's something important to know. Anytime we talk about nuclear decay and half-life, it is a first order reaction. Half-life is the required time for half of a radioactive or unstable substance to become something else. To find the half-life, read the graph at the half point. So right here, if I'm starting with 1, the half point would be 0.5. If I was starting at 100, my half point would be at 50. So this right here is the and what I'm reading is what the time is. So I just read at the half point, and there's that 1. So that means that would, if it was say 1 second instead of the number of half-lives, let's say this is in seconds. So after 1 second, 1 half-life would go by. That would be its half-life, would be 1 second. Half-life decay is always our first order reaction. And we are going to be talking about half-life a little bit later on. Let's look at a second order reaction. Again, if I was given a data table and not told what type of reaction I have, this is how I would figure out. So I'm going to just pick 2 experiments, and I like to pick one so that there's a larger value on top versus the bottom. So I'm just going to pick the first 2. So I'm going to have the rate of my first one being equal to the rate law constant times the concentration of A raised to the x. Remember, it's the x that we want to find, and we're going to divide it by the second experiment. And then let's put in our numbers. So I have 16 times 10 to the minus 3 divided by 4 times 10 to the minus 3, and that's equal to my rate law constants, and then put in your concentrations, 0.4 to the x and 0.2 to the x. So when I look at this 16 divided by 4, this will go to 4, and that's equal to, I have 0.4 divided by 0.2, so that would be 2 to the x. To solve this, x would have to equal 2. And I would write my rate law. Rate is equal to k, and then a raised to the second power, so, or what I have written right there. But that's how you would find it. When you go to graph a second order reaction, on this one, this is showing concentration versus time, and you see that throughout time the concentration goes down. But what is very helpful, what the straight line for a second order reaction is to graph 1 over the concentration. If it's a second order reaction, this is where you get your straight line graph. The units of our rate law constant are very important. Whenever we have a zero order reaction, your units of K are molarity per second. In a first order reaction, you're just going to have time to the minus 1. So if you're measuring in seconds, it would be seconds to the minus 1. A second order reaction for your K would be molarity to the minus 1 times second to the minus 1. And the third order would be molarity to the minus 2 times second to the minus 1, or the time to the minus 1. And how that is derived is just right here on the slide, so you can stop the video to see how the units are derived. So a lot of times they'll give you what K is, and they'll tell you what the unit is, And if you have this memorized, you'll automatically know how to write the rate law because you'll know if it's a first, second, or third order just based on the units of K. Okay, so we have a data table here. This is the same data table that we looked at before where we noticed that the rate law constant is just that, it is a constant. But let's look at the relationship between rate and concentration. So I want to look at these two columns, rate and concentration. So let's just make some observations. So as my concentration of BR squared, let's look and see how that is changed. It looks to me that it's going down in this chart over time. And let's look and see what happens to the rate. So my rate starts at 4.2 times 10 to the minus 5, and I end up with 1 times 10 to the minus 5. So I see that as the concentration of, in this case, my BR2 goes down, my rate goes down too. If it is given that the rate equals K times the concentration of BR, then how do you find the rate law constant? Let's say it's not given to you. So what you would do is you would pick one line, and then you would solve for your equation, your rate law. So if I rearrange my rate law, so K is equal to my rate divided by the concentration of BR2. And then I just pick a line. So I'm going to just pick the first two. 4.2 times 10 to the minus 4 divided by 0.0120. And when you work it out, and I know what it is because they already tell me what it is. But I get 3.5 times 10 to the minus 3. So that is what my K equals. And because this is a first order reaction, then I know that it's going to be S to the minus 1 is going to be my unit. And how that all works out, I'll write it in a different color so you can see it, is this is molarity per second. And down here, this is molarity. And so when you divide this number to find K, your molarity cancels, and you're left with 1 over S, which is the same thing as S to the minus 1. So that's how that unit is derived. In summary, we look at the reaction order. The reaction order is determined by the exponents, and the exponents indicate how the rate is affected by the concentration of each reactant. In a zero order reaction, the concentration changes, but the rate will stay the same. And usually you don't put the concentration in the rate law. Instead, the rate is just equal to the rate law constant. In a first order reaction, if the concentration doubles, then the rate doubles. If the concentration triples, then the rate triples. So you would write it rate equals the rate law constant times whatever the concentration is. In a second order reaction, if the concentration doubles, the rate quadruples. If the concentration triples, the rate increases by 9 times, and you write with the total of your exponents equaling 2. Let's look at an example with a data table with not one reactant but 2 reactants. And I'm going to show you how you can pick which experiment to look at for each reactant. So to start off with, I'm going to pick one reactant, and I want to pick the experiments to use where the opposite reactant, nothing is happening to it. So that way I know that what's going on is just affecting the reactant that I want to look at. So for example, I want to look at my F2 first. And so I'm going to look down, and I'm going to look over at the other reactant. I'm going to see when the concentration stays the same. And I see that it stays the same with experiment 1 and with experiment 2. So those are the 2 experiments I'm going to use. Looking to see which one's bigger than the other, I see experiment 3 is larger than experiment 1. So I'm going to put experiment 3 on top. So 3 goes on top, 1 goes on the bottom. Okay, so that's kind of what I'm going to do. So let me write my expression. So I have the rate of 3 is equal to the constant 3 times the concentration of my F2, because that's what I'm looking at. And it is a good practice to put in the other one. ClO2, and this time I'm going to put to the Y. And then I'm going to have the rate of my first one that I'm going to look at divided by rate law constant, which is 1, and then Fe2 to the X, ClO2 to the Y. Now let's put our numbers in. So the initial rate of the third would be 2.4 times 10 to the minus 3, and that's divided by 1.2 times 10 to the minus 3. I've had students that say they can just look at it to figure it out, but I would encourage you to write it out this way so that you don't make mistakes. Okay, so I got it all written out, and let's go ahead and simplify it. So I'm going to cancel this out, and I get a 2. And then over here on this side, these two things are the same. So that's why I want to pick the two experiments where the concentration stays the same so I can cancel them out. And then let's look at, I have 0.2 divided by 0.1 raised to the x, so that would be a 2 to the x. So I know that x equals 1. So as far as my rate law goes, here's a general rate law that I can write for this that just has both the reactants in it. Remember, you only put reactants into the rate law. And I know that x is now a 1, so I can go ahead and put that in. So this is a 1 right there. Okay, we have one more to do, and this is going to be looking at the ClO2. So I want to pick two experiments where now the other reactant stays the same. And I can see that the reactant stays the same with the first and second experiments. And it looks like I'm going to put the second one on top and then the first one on top. So, okay, so I have the second one divided by the first one. And let's just put in our numbers now. So I kind of ran out of room, but this is, it worked out. So I have 4.8 times 10 to the minus 3 divided by 1.2 times 10 to the minus 3. And when I work that out, that becomes a 4. So I have 4 is equal to, I can cancel all this out. And then as far I have 0.4 divided by 0.1 to the y. So I'm going to have 4 to the y. So what would y be? What does that number have to be to equal 4 equals 4 to the y? It's going to be a 1. So then I can put in my rate law that this y is a 1. Okay? So I'm just going to clear this so I have some more room on this slide. So I now know that my rate law is the constant times f to the 1 times ClO2 to the 1. And you don't have to draw the 1, so maybe I'll just get rid of those. Okay, so we can go ahead, but there's our rate law. Okay, so that is question 4. What is the rate law? And then question 5 says, what is K? So to 5K, you just find one of the experiments. So I'm just going to pick my first experiment. You could pick 2 or you could pick 3, doesn't matter. And you just plug it into your rate law that you just found. I am first going to rearrange the equation so I can have K just on one side. So this all cancels and I'm left with K is equal to the rate divided by each of these concentrations. Remember, the brackets mean molarity. And then I can just go ahead and put my numbers in. So doing our math, I get 1.2, and let's figure out our units. So this m's on top and this m's on the bottom. So I end up with this m that's on the bottom, so that would be m to the minus 1. And then I have this s that's in the denominator, so that would be s to the minus 1. And that's what my k is equal to. So again, find each of the concentrations by picking experiments where the other reactant is staying the same. And just work through them just like I showed you, where you put the rate laws on top of each other. And if you do it this way and not rely on just analyzing the data, you will not make mistakes. So make sure that you write it out this way. So let's do another example doing the same thing. So we're going to find the order with respect to A and with respect to B, and then we're going to write the rate law. So kind of what we did the last time. This is just breaking it up a little bit. So I'm going to start with A, and I want to see when B stays the same. And it looks like B stays the same for trial 2 and 3. And do I have a bigger number there? It looks like 3 has a bigger number than 2, so I'm going to put that one on top. The rate of 3 compared to the rate of 2. And then let's plug in our numbers. So let's simplify. So this will go down to 1. And my rate laws can cancel. Those y's can cancel. So I'm left with 2 divided by 1. I'm left with 2 to the x. So in order for this to be 1, then x has to equal 0. So what is the order with respect to A? It's a zero order reaction. So this means that if A changes concentration, then that does nothing to the rate. And you can see that. If B stays constant, I change the concentration of A, it does nothing to the rate. So that makes sense. So it's a zero order with respect to A. I'm going to erase this so I have room to do my B now. All right, so for my B, I'm going to pick the two that are the same on the other one. So I'm going to pick experiment 1 and 2 to look at. And is there bigger numbers? It looks like there's a bigger number with experiment 2 versus 1, so I'm going to put that one on top. Let's put our numbers in. So let's simplify. So this ends up being a 2. And my k's can cancel. All those 1 to the x cancels. And I'm left with 2 to the y. So I know that y equals 1. So that is a first order reaction for B and a zero order with A. So let's go ahead and write our rate law. So I'm just going to erase a little bit just to clear this up. So my overall order of reaction would be a 1 because 0 plus 1 is 1. So write the rate law. I'll go rate is equal to K times the concentration of B, and I'm done. So it's just B to the 1. Remember, A is just a zero order, so it's not really in there. And then let's go ahead and solve for K, and you can use any experiment that you want. So rearrange this equation, I get K is equal to rate divided by B, and I'll just pick top experiment. So so my molarity cancels, and my K is 1.25 times 10 to the minus 2, and it's s to the minus 1 as the unit. That's what K is. Here's just an extra twist on this. What is the rate if the concentration of A is 3 and B is 3? So I'm going to plug that into my rate law. Let me just clear off a space. So my rate law that I just wrote is K times B. I know what my K is. 1.25 times 10 to the minus 2. And it's an s to minus 1. And I multiply it by B. It doesn't matter what A is, but B is a 3 molar, and I get 3.75 times 10 to the minus 2, and my units are molarity per second. So stop and do one of the problems that's in your packet. You could do question number 20 or one that's close to that.